In this video, we are going to talk about masers. A maser is just short for microwave amplification by stimulated emission of radiation. And this may sound new to you, but I'm sure you've heard about lasers before. A laser is simply a maser that works at higher frequency photons in the ultraviolet or visible light spectrum. So in order to understand how masing works, we need to know about a few processes. The first one of these is when you have an atom and it has a ground state and an excited state, and we're currently in the ground state. When a photon comes in to interact, it can be absorbed if it has the exact frequency nu that corresponds to the energy level h nu between level 1 and level 2. This phenomenon is called absorption. Atoms don't like to stay in high energy states, so after absorption, they will emit a photon and de-excite down to the ground state again. This is called spontaneous emission. Normally, the time it takes for excited atoms to de-excite is about 10 to the minus 8 seconds, but sometimes this time can be as long as 10 to the minus 3 seconds. These states are called metastable, and these emission levels are essential for a maser. When a photon with the absorption frequency is fired at an atom already in its excited state, the atom absorbs this photon and quickly emits 2 photons to get back to its lower energy state. And thanks to quantum mechanics, both of these newly emitted photons are of the same frequency. This is called stimulated emission. Stimulated emission is the fundamental physical principle motivating the maser. Basically, a maser sets up a series of atoms or molecules and excites them to generate a chain reaction or amplification of photons. Say you have a photon coming in here with frequency nu, undergoing stimulated emission at the first atom, sending out another photon here and another photon here. And these two will make 2 atoms able to undergo stimulated emission. And so we get an exponential increase in the number of photons. Since all the resulting photons are of the same wavelength nu, maser beams are extremely focused and coherent. Masers and their shorter wavelength counterparts, lasers, have many practical applications, especially in science and medicine. Cosmic masers can occur in dusty star-forming regions that are cold enough for these molecules to form. The dust's black body radiation in the infrared band is absorbed by these molecules, and a population inversion is established. When maser emission is caused via stimulated emission, these clouds can get very bright, meaning a brightness temperature of power 14 kelvins. Say we have a slab of molecules that are distributed homogeneously in the slab, and they are only in 2 energy levels, E1 and E2. The intensity can then be expressed in terms of the radiative transport equation as I nu equals S nu 1 minus e to the minus tau nu, where I nu is a specific intensity, S nu is the source function, and tau nu is the optical depth. The source function is given as J nu over alpha nu, where J nu, the emissivity, is given as the number density in the second level times the Einstein A coefficient times h nu as the energy and times the line profile function over 4 pi. And alpha nu is h nu over 4 pi phi nu times number density in the first energy level times the Einstein B12 coefficient minus number density in the second level times the Einstein B21 coefficient. And this one is the one corresponding to stimulated emission, while this corresponds to absorption. So altogether, this gives us an S nu equals N2 over A21 phi nu H nu over 4 pi divided by H nu 4 pi phi nu times N1 B12 minus N2 B21. Now if we recall the Einstein relations, G1 B12 equals G2 B21, where G is the degeneracy in the corresponding level, and we have the other relation A21 over B21 equals 2h nu cubed over c squared. And this tells us about the relationship between how many of the atoms will undergo spontaneous emission versus stimulated emission, which is quite important. We'll end up with a source function S nu equals 2h nu cubed over c squared 1 over n1 over g1 g2 over n2 minus 1. When we did this, we assumed that the atoms in our slab are in an excited state, which we more precisely can refer to as a population inversion. How do we get a population inversion? A two-state system will not cause a population inversion due to the principle of detailed balance. But if you look at a three-state system, we have that frequent collisions will cause the atom to be excited from the ground state up to the second excited state, and thereafter spontaneously de-excite into the first excited state. They will then continue to de-excite, but if we have the conditions for stimulated emission to happen, we need to have a fast de-excitation down to the first excited state and then a slow transition to reach the ground state, causing a lot of atoms to still be in the first excited state. And this is when we get population inversion and we have the right conditions for stimulated emission to happen. In nature, we usually see four-state maser systems, which will look and behave similarly, only with an extra level. If the population per degeneracy level in the ground state energy is given by N1 over G1, and this is smaller than N2 over G2, then we will have that N1 G2 is smaller than N2 G1. And if we look at our source function from earlier, that implies that our source function will be negative. That's quite strange, but it gets even stranger. If we look at our optical depth tau nu, which is given as alpha nu, times L, which is just the distance, we will have the optical depth given as h nu over 4 pi times phi nu B21 N1 G2 over G1 minus N2 times L. And this will be equal to h nu over 4 pi phi nu B21 N2 times N1 G2 over G1 N2 minus 1 times L. And here again we see this term that if N1 G2 is smaller than N2 G1, then we have that also the optical depth is negative, which again is really strange. You might think it sounds like physics is breaking down under the conditions of masing, but it's important to remember that the optical depth and the source function are not observable physical quantities. They're rather just record-keeping objects. What we do care about is that our specific intensity is still positive. And if we recall that our specific intensity I nu is given by the source function 1 minus e to the optical depth, so that if tau is negative and if tau is a lot smaller than 1, then we will have that I nu is just the product of S nu and tau nu, and the product of two negatives is a positive. Then we are still good. And also, when tau is not very small but is rather negative infinity, then we have that I nu becomes minus e to the minus tau nu S nu, giving us a specific intensity much larger than 1.